All right, so in this section, we'll be looking at reactions of our organometallic reagents with esters and acid chlorides. So we can take these organometallic reagents and react them with our carboxylic acid derivatives, and our preferred ones are going to be esters and acid chlorides. Now, there are other carboxylic acid derivatives that we will talk about later, but these two tend to be the best for doing this particular type of reaction. So if we use an acid chloride or an ester, then we can get our organometallic reagent to come in and react with that to give us either a ketone or a tertiary alcohol. Now, if it gives a ketone, what that means is that we're going to do a nucleophilic substitution on this, and we'll get the ketone. If we get the alcohol, this tertiary alcohol, what that means is that we're coming in and doing the nucleophilic substitution to get the ketone, and then that reacts with another equivalent to give us the alcohol. So we want to look at both of those possibilities. The key difference between those is if we want to make just the ketone, we need to use one of our reagents. And if we want to do the tertiary alcohol, we can use the other two of our reagents. So this is where the organocuprates are going to come into play. So for the esters and acid chlorides, if we treat them with the Grignard reagent or the organolithium reagent, it's going to react 2 times with that. The first time it's going to do nucleophilic substitution, so it'll do nucleophilic acyl substitution, and then the second time it will do nucleophilic addition, and you will end up with a tertiary alcohol. All right. And so here is a specific example. Here we've got the acetyl chloride with this ethyl Grignard, 2 equivalents, and so you'll see that we add 2 equivalents of that Grignard to that acid chloride, so we'll have 2 ethyl groups on there. On this one, we have the methyl Grignard and an ester. We can add 2 equivalents of that methyl Grignard, so you'll notice that we now have 2 methyls that were attached to this. So we want to think about this as what ester can we use to make this? Like what ester could we use to make this, and then what Grignard could we use? So we're going to kind of think about this a little bit retrosynthetically. So let's go back over to our in-class assignment and look at number 59. So the key is that you want to find the carbon that has the OH, which is clearly this one. And if you can find 2 things that are identical, those things are going to be what the either Grignard or organolithium reagent were, and the rest of it is going to be your aldehyde. So if we're thinking of this retrosynthetically, we would write it like this. So 1, 2, 3, 4, 5. We've got that aldehyde. We've got not an aldehyde, we want ester, so an ester of some sort. It doesn't really matter what our ester was, so I'm just going to put an ethyl group on there, but you could put a methyl group. And then for the Grignard, I'm going to put CH3MgBr, and we would want 2 equivalents of that. We want 2 equivalents of that to react with this to give us that particular reaction. Now, we would subsequently need to protonate with water, but this is a retrosynthesis, so we're just trying to come up with these 2 components. On this next one, the identical groups are these. So 1, 2, 3, 4, they're butyl groups, and our ester is going to have 2 carbons here, and then some sort of other component to make the ester. So we'll do 1, 2. There is our carbonyl. Again, I'm just going to choose the ethyl ester. So this is ethyl acetate, readily available, easy to get. And then we'll need 2 equivalents of the Grignard. So 1, 2, 3, 4, MgBr. And that would add 2 times, and we would get this. Again, we would need water to protonate this. Also, it's worth mentioning that we could use the organolithium reagents in place of these, and that would work just fine. All right, so that's how we can think about it when we're doing synthesis of our tertiary alcohols with esters and acid chlorides and either a Grignard reagent or a organometallic or organolithium reagent. We're going to look at the mechanism of the nucleophilic, actually we're going to do both a nucleophilic substitution and a nucleophilic addition. So in our first step, we're going to take our either acid chloride or ester and treat it with a organometallic reagent, an organometallic reagent. In this case, we're going to choose Grignard. That Grignard comes in, reacts, and gives us this tetrahedral intermediate. The tetrahedral intermediate automatically, it will lose this leaving group, which is either the alkoxide or the chloride. We're going to lose that leaving group and form a ketone. That ketone is very reactive to Grignards and organolithium reagents. So if there's some there, it will react with that ketone. And when it does, we will again form this tetrahedral intermediate that's an alkoxide. And so in a final subsequent step, we would add some water to protonate that alkoxide to give us our tertiary alcohol. So that's our mechanism. You'll notice that we're doing both a nucleophilic substitution in steps 1 and 2 and a nucleophilic addition in steps 3 and 4. So it's both nucleophilic substitution and addition. Now, on all of those where we did both the nucleophilic substitution and the nucleophilic addition, you'll notice that I used either Grignard or organolithium. And up to this point, I've been telling you, oh, the organocuprates, they're less reactive. Well, now we're finally going to talk about these organocuprates. So if we want to form a ketone from either an ester or an acid chloride, then we're going to need to use a less reactive reagent. And the less reactive reagent is our organocuprate reagent that I have been hinting about for a long time. So the organocuprate will react with this. So it will react with our acid chloride. It will do that first step where it does the nucleophilic substitution, and then we'll have a ketone. And then to get rid of any of the remaining organocuprate, we'll add some water, and that just sort of cleans things up, and we'll have our ketone as our product. Here is a specific example. So here we have this diethyl cuprate, and one of those ethyls is going to come in, react with this, and replace that chloride. So here is our ethyl that has replaced the chloride. And again, the water is just sort of to clean everything up. Now, what we're going to find is that, yes, if we do this, I think I misspoke a minute ago. If we do this with an acid chloride, this works pretty readily. If we attempt to do this with an ester, we're not going to have as much luck because the esters are a poor leaving group. So I think I misspoke a minute ago when I was talking about this. So let's look at what acid chloride, or not what acid chloride, what's going to be made when we use an acid chloride. So here we've got number 27. We'll come back over here. What organocuprate reagent is needed to convert this acid chloride into each of these ketones? Now, on each of these, there's more than one possibility, and I am going to pick the better possibility. So first of all, so let's look at this acid chloride. Since we have the acid, we only have this acid chloride, that really means that we only have one option here. And the one option is, so I'm going to go ahead and draw this. 1, 2, 3, chloride. So since we only have one synthetic option. So if this is our acid chloride, then we need to cut this one here. And that means that this would need to be our Grignard. So our Grignard, or not our Grignard, our organocuprate, It's going to be the CH3, CH2, CH, I'm going to put this in parentheses, CH3, all right, and then this is what's bonded. This particular carbon is what's bonded to the copper lithium. So that looks weird, but this is a sec-butyl, it's a sec-butyl organocuprate. So we'll take that sec-butyl organocuprate and we will make that. All right, on this one, this is where we're going to cut it. And so again, that will be our acid chloride, and our organocuprate is just going to be the phenyl. So it'll be C6H5 2 CuLi. And that will give us our product. All right, well, we can react the Grignard, we can react the Grignard with the carbon dioxide, because carbon dioxide has it does have an electrophilic carbon. So on the carbon dioxide, the carbon has a significant partial positive charge, which makes it susceptible to nucleophilic attack. That nucleophile will come in and react and give us this intermediate, which is going to be the carboxylate. We will need, instead of just adding water, we will need to add a mild acid to protonate this. And so when we add that mild acid, we will end up getting the carboxylic acid. We call this reaction carboxylation. It adds one carbon to the chain. So we're going to take whatever our Grignard reagent is, and we're going to add COOH to it. So we're going to turn it into a carboxylic acid. All right. We can react organometallic reagents with epoxides. And again, this really only, this works, in this case, it will work with all of our organometallic reagents. It'll work with the organolithium reagent, the Grignard reagent, and even the organocuprates. They will open up the epoxide rings to form alcohols. So here we can react with one of these carbons. It'll do a ring opening of that epoxide group. When it does, that's going to form an alkoxide, so we'll need to protonate. And if you go back to the chapter 9, which was all about alcohols and ethers and epoxides, you'll look at similar reactions to this. We will get these kinds of reactions occurring, where a nucleophile comes in, does an SN2 to open up that epoxide. Here we've got a specific example where we just have ethylene oxide. We treat it with the phenyl Grignard reagent and water. That will open up our epoxide and give us this primary alcohol. Now, we do have some regiochemistry if we've got substituents on the epoxide. So I'll go ahead and show you the picture. So it is a two-step process. The first step is an SN2 reaction of our organometallic reagent on the carbon. So it'll come in and react. Since it's SN2, and since this is under a very basic conditions, that nucleophile is going to go to the less substituted carbon because it is less sterically hindered. And this is a very common thing we've seen with epoxides in basic conditions. Again, if you go back and compare this to when we did epoxide ring opening in chapter 9, you'll see that when it was under basic conditions, it went to the less substituted carbon. And when it was under mildly acidic conditions, it went to the more substituted carbon. Well, we can't do the mildly acidic conditions with these organometallic reagents, so it's always going to go to the less substituted carbon. All right, and I just realized that it was not number 37, it's number 31. That is our in-class assignment problem. So let's come back over here. All right, what epoxide is needed to convert this ethyl Grignard to each of the following alcohols? So we need to know what epoxide. In this case, the epoxide is simply going to be the cyclohexane epoxide. All right, so if we use that epoxide and we have this come in, we will find that the alkyl group, our Grignard reagent, will come in opposite the side of the alcohol, which is why these end up being trans to each other. So if we just use that epoxide and then follow it with water, quench it with water, we will end up getting that. As far as this particular alcohol, we want the epoxide to be here, and this is our new carbon-carbon bond that we have formed. And so we're going to make that our epoxide and this as our Grignard. So because this comes into the less substituted carbon, that ethyl group will come in here and react. Will come in here and react with this. It'll open it up so the OH will go to this particular carbon and quench it with water, and we will get that. And then finally on this one here, again, this is the new bond that we're going to make. So this is the oxygen from the epoxide. This is going to be the other carbon in the epoxide. So our epoxide is simply going to be this. That ethyl Grignard will come in and react with the less substituted carbon. It'll break this bond. The OH will come over here. We protonate it, and we'll get this particular alcohol. So now we want to talk about Alpha Beta-Unsaturated Carbonyl Addition. And this is kind of neat because here we can do addition either directly to a carbonyl or to the alpha beta unsaturated bond adjacent to that carbonyl. And again, which reaction occurs depends on which reagent you choose. So this particular compound, if we draw the resonance structures for this, we will see that we can draw one resonance structure that puts a positive charge on the carbon. That carbon is very electrophilic. We can draw another resonance structure that puts a positive charge on the beta carbon. The alpha carbon won't get the positive charge, but the beta carbon will. That means that there is a partial positive charge on the beta carbon. So it's possible that our nucleophile can either come in and react with the carbonyl, or it can come in and react with our beta carbon. And that's because of the partial positives there. Which one it reacts with depends on which reagent you choose. If it reacts with the carbonyl, we're going to refer to that as 1,2 addition. So if we get reaction directly with the carbonyl, we're going to refer to that as 1,2 addition. It adds across these two bonds, and the additional pi bond over here is completely unaffected. So that's going to be 1,2 addition. If we get addition to the beta carbon, we're going to refer to that as 1,4 addition. So here we're adding it to that beta carbon. We end up adding across these two bonds, so it looks like 1,2 addition, but I'll explain why it's 1,4 addition in a minute, and it has to do with it's this whole system. But 1,2 addition for direct carbonyl attack, 1,4 addition for beta carbon attack. So let's look at the mechanism for 1,2 addition. So this is exactly the same as we see for nucleophilic addition for any aldehyde or ketone. There's not any difference except that there happens to be a carbon-carbon double bond on the compound that we're not going to react with. So here in the first step, we get nucleophilic attack of our nucleophile on the carbonyl. And then in a subsequent second step, we add water to protonate that and give us our alcohol. And that's all there is to it. This is no different than the mechanism we saw previously for nucleophilic attack on an aldehyde or ketone. For 1,4 addition, it's a little bit more complicated. So in our first step, the nucleophile comes in and reacts with the beta carbon. Remember, there is a partial positive charge on that beta carbon because of our resonance structures. So it comes in and reacts with that beta carbon, and that puts a negative charge here on the alpha carbon. There are two resonance structures we can draw for that. One is this one, and with that one we have the negative charge on the carbon, and if we just protonate that carbon, we'll get this, and that will be our product. However, what more likely happens is that we, because there is another resonance structure where we can put the negative charge on the oxygen, that will be the more significant resonance structure. We put the water in, that comes in and protonates that oxygen and gives us this enol. Well, as we saw back in chapter 11, chapter 11, when we have an enol, it will undergo tautomerization, or it will tautomerize, if we want to make that into a verb. So the tautomerization of this, and it will give us this, putting the hydrogen on that alpha carbon. So both of these give the same result. It probably goes through this mechanism, but it doesn't really matter. We call this 1,4 addition. And the reason we call it 1,4 addition is because of this. We've added the nucleophile to one carbon, and to the 4 position, we've added the hydrogen. Then it tautomerizes, and we get our alpha beta addition. So which carbon the nucleophile attacks is going to depend on which reagent you choose. If you choose an organolithium reagent or a Grignard reagent, you're going to get attack 1,2. You're going to get attack at the carbonyl, which will give us the 1,2 addition product. So here it just ignores that conjugated pi bond there, and we're going to get direct attack at the carbonyl. So again, that's with our organolithium reagent or the Grignard reagent. Either one of those will work. For organocuprates, we will get 1,4 addition. So here we've got a generic organocuprate. It comes in, reacts with the beta carbon, and we end up getting 1,4 addition. So we get beta attack of our nucleophile. Here is a more specific example. So the nucleophile will come into this beta carbon here, and we will get a methyl there and a hydrogen adjacent to it. And that is going to be our example of 1,4 addition versus 1,2 addition. Well, let's look at number 40. All right, we want to draw the product. You'll notice that we've got a carbonyl and an alpha beta unsaturated. And I'm going to go ahead and label this. This is the alpha carbon. This is our beta carbon. All right, and we want to understand what's going to happen with each of these reagents. So all of them are going to start off with A. So compound A, which is this thing. And if we do reagents A, which is sodium borohydride, well, sodium borohydride is a reducing agent. It will reduce only that ketone. And so we will end up with an alcohol. All right, that alcohol will be an allylic alcohol. I'm going to redraw this. All right, I think I made it worse. Anyway, we will have an allylic alcohol, but we will have an alcohol here because we're reducing. All right, next we're going to reduce with catalytic hydrogenation with one equivalent of hydrogen. Now, you may or may not remember this, but when we do hydrogenation of an alpha beta unsaturated, it's going to do the carbon-carbon double bond first. So again, A, condition B, and we're going to hydrogenate the carbon-carbon double bond, but we will leave the carbonyl unaffected. So we will hydrogenate that. All right. If we do two equivalents, so this is reaction conditions C, that's going to hydrogenate both the carbon-carbon double bond and the carbonyl. So in that case, we're going to end up with an alcohol. And we will have no double bonds remaining. All right, for reaction D, this is an organolithium reagent. And just as a reminder, organolithium reagent is a stronger one. It will go directly for the carbonyl. All right, so that organolithium reagent will react with that carbonyl. So the carbon-carbon double bond will be unaffected. So we'll still have that carbon-carbon double bond, but we will now have this tertiary alcohol. Started off with a ketone and a organolithium reagent, and that gives us a tertiary alcohol. All right, here we've got the Grignard reagent in a very similar fashion. The Grignard reagent will, because it's a strong nucleophile, it will react with the carbonyl preferentially. So this is reaction E, and that is the ethyl Grignard. So all right, so our carbon-carbon double bond will remain intact, and we'll have the methyl OH, and then there is our ethyl. That's the group that we added. And then finally, we'll start off with compound A, and we'll go to use these conditions. And this particular one is, we've got a vinyl organocuprate. Organocuprates prefer to do addition to the beta carbon, so we will get attack on that beta carbon. And our carbonyl will remain intact. So we'll get attack on that beta carbon with this nucleophile. We'll add that. We'll have no more double bond there, but we will have a double bond here because we have added that double bond. All right. We're getting close to the end here. So we want to look at this summary for organometallic reagents. All right, so when an organometallic reagent attacks an electrophilic carbon, it's very good at attacking electrophilic carbons, and it can be either a carbonyl carbon, all right, and it could be a carbon dioxide, or it can be an epoxide. All right. What happens after it attacks depends on what else is attached. If we've got a leaving group, we can do nucleophilic substitution, and if we've got something that is a poor leaving group, then we can do nucleophilic addition. So for aldehydes and ketones, we will end up getting the addition product, and for esters and acid chlorides, we will get the substitution product. All right, we'll find that the organolithium reagents and the Grignard reagents are very reactive, and that the organocuprates are much less reactive, which gives us some selectivity on certain kinds of reactions. So now let's look at synthesis. How do we do this all and do some synthesis? All right, so knowing your oxidation and reduction reactions is very useful, and we've talked about some of these before. We can convert a functional group to a good leaving group, and then allows for other reactions to occur. And then we need to know what kinds of things we can do with an alcohol. So for example, here, if we've got an alcohol, there's all kinds of reactions that we know how to do with this. We can take that alcohol and do an elimination. Now, we will get this product, but we're also going to get some other products, so this one's kind of messy. We can convert that into a ketone using one of our mild oxidizing agents like pyridinium chlorochromate, or we can use one of the stronger ones like chromic acid. Any of those will work. And there are a few other reagents that we can do to convert to a ketone. If we want to convert this to to an alkyl halide, there are a couple of options, HCl, HBr, that's where we'll protonate this. If you're not familiar with this, go back and look at chapter 9. All right, thionyl chloride or PBr, this will convert it to a chloride, this will convert it to an alcohol or to a bromide. Again, go back and look at chapter 9 for that one. Toluene sulfonyl chloride, if we treat this with toluene sulfonyl chloride and pyridine, we'll get the toluene sulfonyl ester, so that sulfonate, and we can treat that with a nucleophile and we can get this. Now there's some stereochemistry that's interesting that can happen with these, and you'll need to go back and review those if you want to remember which one of these does SN1 and which one of these does SN2. Hint, the SOCl2 and PBr3 do SN2, and the HCl and HBr do SN1. This retains the chemistry, and then when you do the nucleophilic substitution, you'll invert the chemistry. So, but if you need to, go back and review chapter 9 for that. So let's look at a practice problem. We want to synthesize 1-methyl cyclohexene from cyclohexanone, and we can use any organic alcohol. All right, so to do this, since our limitation is an organic alcohol, that means that we're going to need to do some conversions to convert that alcohol into one of our reagents. So here we've got the methyl Grignard, and we want to get that from cyclohexanone. You'll notice that we're adding a carbon here, and because we're adding a carbon, that means that we're going to need to use one of our organometallic reagents, preferentially an organolithium reagent or a Grignard reagent. So form the double bond from alcohol dehydration. That would be our first retro step. So we can get this double bond from doing dehydration. And then this is a tertiary alcohol, and we know that we can make that from this ketone using a Grignard reagent. The Grignard that we're going to choose here is going to be the methyl magnesium halide. And so in this case, that methyl Grignard we can get from the alcohol. And there's 2 steps that we would have to do to get that. So let's turn it all around and do the entire synthesis. All right, prepare the Grignard from the methanol, and I'll talk about that. So now let's write out the entire synthesis. First, we're going to need to convert the methanol into an alkyl halide. And we can do that with HBr or PBr3. Either one of these will work. They're both going to be SN2 reactions. So here we've got methyl bromide. We can convert that into the Grignard reagent using just putting magnesium in there. In addition to that, we could use lithium and create an organolithium reagent. That would work as well. And then from that we could get we can add water, or we can add that to the cyclohexanone, add water as a second step to protonate to give us our alcohol. And then from this we could use sulfuric acid to eliminate. All right, we could eliminate, and this would be our major product. We would get a little bit of this minor product, but we should get mostly this. If we're trying to get this, there's another way to do that, and we're going to talk about that in chapter 18. But let's look at chapter 17, number 68. It's our last problem here. And this is our last slide. So we want to devise a synthesis for this E-tetradeca-11-enal. And this is a somewhat involved synthesis. So we want to get this from from this bromine alcohol compound. So we're going to draw that out, and then any organic chemicals and inorganic reagents that we need to add the additional stuff. So let's draw this. We've got 10 carbons, an OH on one end, and a bromine on the other end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on one end we've got the OH, And on the other end, we've got the bromine. So when thinking about this retrosynthetically, we could get this compound. We can get this compound from, and I'm just going to call this compound A. We can get compound A retrosynthetically from this compound. So 1, 2, 3, 4. All right, so there we've got that particular carbon-carbon double bond and that alcohol. We know that we can convert alcohols into aldehydes using PCC. All right. Well, now how do we make this? Well, we can make this from our let's see, we can make this from a alkene. We can convert the alkyne into an alkene by doing a reduction. So again, we'll do a retrosynthesis arrow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. OH. So again, we can reduce this to this, and then we can get that from our original compound up here. Now we're going to need to do some what do you call it? Protecting group chemistry. So 1, 2, 3, 4, 10. We're going to need to do some protecting group chemistry to make this, but that should be relatively straightforward. And then the reagent that we're going to end up using is going to either be an organolithium reagent or an organosodium reagent. We can do something like this: CH3, CH2, carbon triple bond carbon, lithium. And then either one of those would work. But as I mentioned, we're going to have to do that from do some protecting group chemistry. So let's start by making this. We're going to make this particular organolithium reagent. All right. So we could take acetylene, and with acetylene, we could treat this with something like CH3Li. So that's going to be our methyl lithium reagent, and that will give us this H, C triple bond, and we'll just put this as lithium. And then that particular lithium reagent, we can treat that with ethyl bromide, and that would give us that organolithium reagent. And we're going to use that in a minute. All right, I had to pause there for a second. A train came by and decided it wanted to honk its horn, sing its song to its other trains. Okay, so now let's get this all set up. We're going to take our original compound, which was way up here, which is this bromine and alcohol, and we're going to need to protect it before we treat it with this. So we'll take the Br 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 OH. We're going to treat that with the TBDMS chloride and imidazole. And then that is going to give us this, the bromine, 2, 3, 4, 5, 6, 7, 8, 9, 10, O, TB, DMS. All right, that we can treat with our organolithium reagent, and it will do a reaction. We can also treat it with a organosodium reagent, and we could treat that, and we would get this. So 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. O, T, B, D, M, S. All right. With that, we can treat with sodium and NH3, and that is going to do a stereoselective reduction of this, where we will get the trans product. And we'll get that. All right. We can then, we need to remove our TBDMS. So we can use the tert butyl, the tert butyl. So we'll do Bu4N plus F minus. So the tert butyl ammonium fluoride. And that will get us to the alcohol. Three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so we have a double bond there and OH there. And then finally, if we treat that with pyridinium chlorochromate, we will get our final product, which will be 6, 7, 8, 9, 10, 11, 12, 13, 14. That aldehyde, just like that. All right, so you might want to pause, go back, look at that one a little more carefully. That's an involved synthesis, but that is the kind of thing you can do once you have memorized a bunch of your reactions. So keep working on those reactions, and I'll see you for chapter 18.